The architectural thesis, control versus enforcement. Many security architectures contain a fundamental flaw. They tightly couple decision and enforcement. Systems become brittle, hard to scale, fail unpredictably under load or attack. Zero Trust is a decision system, not a product. It evaluates signals and renders an access verdict. Resilience depends on clean separation. Decouple the control plane from the data plane, the three-part architecture. This separation is not a minor detail. It's the central principle for enterprise-scale security. This discussion is for practitioners. Assume identity networking cloud fundamentals. Focus, architectural principles, not products. We'll analyze why systems succeed or fail in real-world environments, design trade-offs, operational consequences. No buzzwords. Provide a vendor-neutral reference model. Move from principles to impact on security operations, incident response, maintaining control during a crisis. Conflating control and enforcement is a pervasive mistake. Use a consistent mental model. Imagine a flow. It begins with signal sources. Input, identity. Input, device health. Input, behavior. Signals go to a decision plane, the control plane. A policy decision point, PDP, evaluates signals against policy and produces a verdict. Verdict, allow verdict, deny. Verdict is transmitted to an enforcement plane, the data plane. A policy enforcement point, PEP, applies the decision mechanically without re-evaluating the logic. This three-part flow underpins resilient architecture, critical for security architects, senior engineers, SOC leaders. Fusing control and data into a monolith lets a single failure cascade. DDoS against decision logic can disable enforcement. Misconfiguration in the policy engine can take down networks. Decoupling gives resilience. Plan for failure modes. Decision plane unreachable. Enforcement point. Fail open. Enforcement point. Fail closed. How long to trust cached decisions? These architectural questions determine if your posture survives contact with reality. The anatomy of a signal. A zero-trust decision begins with a signal. These signals are the raw inputs for our policy engine. They are the evidence upon which an access verdict is built. We can organize them into four primary categories. Identity assertions. This is more than just a username. It is a verifiable claim about who a principal is, packaged in a token like SAML or OpenID Connect. Includes attributes like group memberships, roles, clearance levels, device posture. Describes the state of the endpoint requesting access. Is the operating system patched? Is endpoint protection running and updated? Is the disk encrypted? Provides a health and compliance check on the device. Behavioral telemetry, a dynamic signal capturing patterns over time. Establishes a baseline for normal behavior. Flags deviations. Example, a user who usually logs in from one location in business hours, suddenly authenticating from a new country at 3 a.m. Generates a high-risk behavioral signal. Telemetry can include application-level actions, attempts to access unusual volume of data, or a sequence of failed API calls. It provides context static attributes cannot. It shifts evaluation from a snapshot to a continuous assessment of intent and risk. Contextual signals. Environmental attributes that frame the access request. Network location of the request. Geographical origin. Time of day. Context includes the sensitivity of the resource, a request for a public marketing site, versus a request for the production database containing customer financial data. Data classification labels. API endpoint sensitivity. Network segment. These four signal types, identity, device, behavior, and context, are the foundational pillars of policy evaluation. Anti-pattern. Over-reliance on a single signal type, most often identity. Only validating credentials without device posture or context is not zero trust. It is simply authentication. True policy-driven access control requires aggregation and correlation of multiple independent signal categories. The strength of the decision is proportional to the richness and diversity of signals. A weak signal, like an unfamiliar location, can be counterbalanced or amplified by strong signals, like a healthy device and a low-risk data target. Signal provenance and trust boundaries. For any signal to be useful, we must be able to trust its origin. This is the concept of signal provenance. It is not enough to receive a signal stating a device is compliant. We must know which system made that assertion and have a reason to trust it. Every signal originates from a source, crosses trust boundaries, and is ultimately consumed by the decision engine. An architect's job is to map this flow and validate the authority of each source. For example, the authoritative source for an identity assertion is the identity provider (IDP). Authoritative source for device posture. Unified Endpoint Management (UEM), Mobile Device Management (MDM). Let's visualize the journey of a signal. An access request originates from a client device. The signal for device posture is generated on that device by a trusted agent. This signal is then sent to the control plane. Here, it is cryptographically verified to ensure it came from the legitimate agent and has not been tampered with in transit. The control plane then fetches an identity assertion from the IDP, again validating its signature. These signals, now validated and residing within the control plane's trust boundary, are combined. The resulting bundle of trusted information is what the policy decision point consumes. The signal's value is directly tied to the integrity of this chain of custody. The most critical points in this flow are the trust boundaries. A trust boundary is any point where data passes from a less trusted system to a more trusted one. When a signal from an unmanaged personal device crosses into your control plane, that is a boundary crossing. A core architectural task is to ensure that signals are rigorously validated at these ingress points. We cannot implicitly trust a signal just because it arrived. We must verify its source. We must verify its integrity. We must verify its timeliness. Without this validation, an attacker can forge signals. They could, for instance, present a stolen identity token, a fabricated device health report, to bypass policy controls completely. This leads to the anti-pattern of aggregating weak signals without considering their provenance. If your system collects 10 low-confidence signals and treats them as one high-confidence indicator, you are building a house of cards. For example, using an IP address. Geolocation is a weak signal. It can be easily manipulated via VPNs or proxies. If this signal is given the same weight as a cryptographically signed assertion from a trusted platform module on the device, the entire risk calculation is flawed. Authoritative signals are those that are difficult for an attacker to forge or manipulate. Effective architecture prioritizes signals with strong provenance over a large volume of untrusted telemetry. Signal quality and operational impact. Beyond provenance, we must consider signal quality. Quality has several dimensions: freshness, accuracy, completeness. Signal freshness is crucial. The state of a system is ephemeral. A device that was compliant 5 minutes ago may have been compromised seconds later. A policy decision based on stale data is an unreliable decision. Define a time to live, TTL, for each signal type. Device posture checks, revalidate every hour. User role membership, considered fresh for a full day. Relying on cached signals without clear expiration and revalidation introduces significant risk. Another aspect of quality, signal replay risk. A replay attack captures a valid signal and resubmits it later to gain access. Imagine an attacker capturing network traffic with a device health attestation. If signals aren't unique and time-bound, they can be replayed from a non-compliant device to fool the decision engine. All signals over untrusted networks must include a nonce or timestamp and be signed. This makes each signal unique to a transaction and prevents reuse. The operational impact on a SOC is immense. Inaccurate signals, stale signals, untraceable signals. These produce a stream of low-fidelity alerts. This creates alert fatigue. Analysts must investigate without clear data lineage. Determine if a signal was legitimate. Determine if it was a false positive. If a device is flagged non-compliant, which check failed? When was it performed? By which system? Without clear signal lineage, investigations stall. Mean time to respond increases dramatically. Signal architecture is foundational to an effective security program. Noisy telemetry means more operational overhead and higher chance of missing real threats. Treat signal ingestion as a critical control point in your control plane. Every signal source must be documented, its authority evaluated, its failure modes understood. SOC capability to detect depends on signal clarity. SOC capability to investigate depends on signal clarity. SOC capability to respond depends on signal clarity. Garbage signals produce garbage decisions and ineffective enforcement. Policy evaluation and risk calculation. Once our control plane has ingested and validated a set of signals, the next logical step is policy evaluation. This is where the core decision-making happens. A policy decision is not a monolithic event. It's a process composed of distinct components. The first is the policy language itself. It's the structured syntax used to express rules. Example rule: allow if role is engineer and device is compliant and resource is non-sensitive. The language must be expressive enough for complex business logic, yet simple to evaluate and audit. Languages like Rego, used by Open Policy Agent, are examples. The clarity of this language is paramount for security and maintainability. The second component is the risk model. A simple binary policy, allow or deny, is often insufficient. A risk model translates incoming signals into a quantifiable score. For instance, a login from an unrecognized IP address might add 10 points. A missing OS patch might add 30 points. The model defines the weight of each signal attribute. That allows a more nuanced, adaptive evaluation. Access can be granted, access can be denied, or access can be conditionally allowed with step-up authentication. This risk model is the intellectual core of the decision engine. The third component is the scoring engine. This engine is the runtime that executes the logic. It takes the policy rules and the risk model, applies them to the incoming signals, and computes the final outcome. The engine must be highly performant, processing thousands of decisions per second in a large enterprise. It also must be deterministic. The same inputs should produce the same output. Predictability is essential for testing, debugging, and post-incident forensic analysis. The scoring engine translates abstract policy into a concrete, actionable verdict. Finally, contextual inputs that aren't part of the primary signal bundle are also essential. This includes threat intelligence feeds that might flag an incoming IP as malicious. It includes a list of sanctioned countries. It could include temporal data, such as a change freeze window during which privileged access is denied. These inputs are often fetched in real time or from a frequently updated cache by the scoring engine. They provide external context that enriches decision-making beyond user and device signals, making the policy aware of the broader threat landscape. Architecturally, there are two primary models for where policy evaluation occurs: centralized and decentralized. In a centralized model, all signals are sent to a global PDP or a regional PDP. This single service or cluster of services holds the canonical policy and performs all evaluations. The primary advantage is consistency, the same policy everywhere. It simplifies policy management and auditing, a single source of truth to update and inspect. Conceptually simple, ensuring uniform enforcement which helps compliance and governance. However, the centralized model introduces critical dependencies. Every access request now incurs network latency. For high-throughput, low-latency applications, that round trip can be unacceptable. More importantly, it creates a single point of failure. If the centralized PDP becomes unavailable due to a network outage, a DDoS attack, or a simple service failure, what happens? Every system that relies on it for decisions may fail. This availability risk is the single greatest drawback. It forces a difficult choice: failing open, which destroys the security promise, or failing closed, which can cause a catastrophic enterprise-wide outage. The alternative is a decentralized or local evaluation model. In this architecture, the policy logic is replicated to the enforcement point itself or to a sidecar running alongside it. The PEP evaluates policy locally, eliminating the network latency and availability dependency of a remote call. This is ideal for performance-sensitive services and for environments where network connectivity may be unreliable, such as edge computing or IoT. The enforcement point can continue to make decisions even if it is completely disconnected from the control plane. This inherent resilience is the model's key strength. It provides a robust and scalable solution for distributed systems operating under diverse conditions. Of course, this model has its own trade-offs. The primary challenge becomes policy distribution and state management. How do you ensure that every one of your thousands of PEPs is running the correct and latest version of the policy? If a policy is updated centrally, there will be a replication delay before it reaches every node. During this window, you have policy drift, where different parts of your system are enforcing different rules. The architecture must include a secure and reliable mechanism for distributing policy updates and a way to verify that the local PEP is trustworthy and has not been tampered with. It trades the risk of runtime unavailability for the complexity of state synchronization. Policy is not static configuration. It is time-sensitive state. The centralized policy store is the source of truth, but the locally cached policy at the PEP is the operative reality. This introduces the problem of state replication and versioning. When an administrator pushes a new policy, for example, to block access from a newly identified malicious IP range, that change must propagate. A robust architecture must have a clear versioning system for policies. Each decision rendered by a PEP should be logged with the specific policy version it used for evaluation. This is not an optional feature. It is a fundamental requirement for incident response and audit. During an investigation, knowing that a decision was made is not enough. The SOC analyst must be able to reconstruct the exact context of that decision. This means logging the incoming signals, the policy version that was applied, and the resulting risk score and verdict. Without this telemetry, it is impossible to answer the question, why was this access granted? If an attacker gained access, was it due to a policy flaw, a stale cached decision, or a compromised signal? The PDP and every local evaluation engine must therefore emit detailed, structured decision logs. These logs are as critical as the enforcement action itself. They provide the observability needed to trust and troubleshoot the system. This dynamic nature of policy also exposes failure modes related to overload. A centralized PDP, even if highly available, has a finite capacity. A sudden spike in authentication requests can overwhelm the decision engine, from a legitimate scale-up event or from a denial-of-service attack. If the PDP becomes slow to respond, every application waiting for a decision also becomes slow. This can cause a cascading failure throughout the enterprise. An architecture must therefore define timeout behaviors and retry logic for communication between the PEP and the PDP. More importantly, the PP must have predefined behavior for when the PDP is non-responsive, typically falling back to a limited locally cached decision. This is where risk calculation becomes dynamic. The trust in a cached decision should decay over time. A decision made 1 second ago is highly trustworthy. The same decision cached for 10 minutes is less so. A sophisticated PP might use a cached decision but add a risk score penalty that increases with cache age. This allows degraded but still functional enforcement, permitting low-risk actions while blocking high-risk ones until the control plane is restored. This fail-safe logic, codified in the architecture, separates a resilient system from a brittle one. The decision rendered by the policy decision point is meaningless until it is acted upon, This action occurs at the policy enforcement point, or PP, which forms the core of the data plane. The data plane is where traffic flows and where access control is actually applied. Enforcement points are not monolithic. They manifest in various forms across the architectural stack. One common form is an application layer agent, a library compiled into an application, a module running within a web server, a service mesh sidecar proxy, like Envoy. These agents intercept requests before they reach the application code, providing granular, per-request enforcement deep within the system. Their proximity to the application allows for context-rich enforcement based on specific API calls or data queries. Another critical enforcement surface is the API gateway, positioned at the edge of a microservices architecture. The gateway serves as a natural choke point for all incoming API traffic. By integrating a PEP at this layer, we can enforce policy before a request even enters the internal network. This is highly efficient for applying broad policies, such as JWT validation, rate limiting, IP-based blocking. Further down the stack, we find data proxies. They operate at the database or storage layer, intercepting queries and enforcing policies based on the user, based on the data being requested, based on the nature of the operation. This allows for fine-grained control, preventing, for instance, selection of columns containing PII even if the user has table access. We can also enforce policy at lower levels of the stack. Host-based kernel modules or agents with deep OS integration can act as PEPs. They can filter network connections at the socket level, or control process execution based on policy decisions from the control plane. This is a powerful model for enforcing workload identity and segmentation, ensuring that only authorized services can communicate with each other on a given host, regardless of network topology. Finally, there are traditional network-level filters, such as next-generation firewalls or intelligent switches. While further from application context, they can serve as coarse-grained PEPs for network segmentation and blocking traffic from known bad sources based on decisions pushed from the control plane. The placement of these enforcement points is a critical architectural decision. The choice between an in-band proxy versus an out-of-band agent involves significant trade-offs. In-band enforcement, where the PP sits directly in the data path, offers the most robust control as it can block traffic inline. However, it also introduces latency and becomes a potential point of failure. Out-of-band controls, like an agent that configures local firewall rules, are less intrusive but may have gaps in enforcement if the agent fails or the underlying OS mechanism is bypassed. A mature architecture often uses a combination of these, layering different PEPs to provide defense in depth across the application identity network layers. The relationship between the policy enforcement point and the policy decision point is governed by a contract. This contract is not just a protocol, latency, availability, behavior under stress. The communication protocol itself must be lightweight and efficient. A simple RESTful API call with a JSON payload is common. The PP sends the bundle of signals. The PDP returns a decision object. This object should not just contain a binary allow or deny, risk score policy version used, and any obligations, such as logging or step-up authentication. A critical part of this contract is defining the behavior during a failure. What happens when the PEP sends a request to the PDP but receives no response? Fail open. Default to allowing access, prioritizing availability. This is often unacceptable because it disables policy control during an outage. Fail closed. Default to denying access, prioritizing security. While safer, it can trigger a catastrophic outage, halting dependent applications. To avoid that binary choice, architectures can implement degraded enforcement modes. This relies on local caching at the PEP. A decision to allow a non-sensitive resource might be honored from the cache for a limited time, but a highly privileged operation would be denied without a fresh PDP decision. The result is graceful degradation, partially functional and more secure than fail open. The logic, what can be cached for how long and under what conditions, is core to the PP's design. This fallback often relies on cryptographic proofs rather than simple caching. The PDP can generate a short-lived signed token like a JWT that encapsulates the decision, known as a signed decision or authorization token. The PEP can validate this token locally without contacting the PDP for every request. This moves the model from synchronous request response for every action to an asynchronous one where the PEP is charged with a set of permissions. This drastically reduces load on the PDP and makes the data plane far more resilient to control plane latency or outages. The communication channel between the control plane and the data plane is an extremely high-value target for an attacker. If this channel can be compromised, the entire policy system can be subverted. Therefore, securing this channel is not an afterthought. It is a primary architectural requirement. The first and most fundamental control is mutual authentication. The PEP must authenticate the PDP to ensure it is receiving decisions from a legitimate source. The PDP must authenticate the PEP to ensure it is not sending decisions to a rogue enforcement point. This is typically achieved using mutual TLS. Both client and server present and validate certificates. Establishing a trusted encrypted channel. Beyond encrypting the channel, we must protect the integrity and authenticity of the data itself. Imagine a man-in-the-middle attacker, even if they cannot break TLS. They could capture a valid allow response from the PDP and replay it to the PEPI for a different request. To prevent this, every request and response must be resistant to replay. Include a unique single-use value, a nonce, in every request. The PDP's response must be tied to that specific nonce so it can't be reused. Another defense, signed policies. The PDP can send a policy object digitally signed by a central authority. The PP, holding the authority's public key, verifies the signature before executing. Even if the PDP is compromised, it cannot push unsigned malicious policies. PEPs will reject any policy not signed by the trusted root. This decouples trust in policy content from trust in the PDP service. From security operations, this channel must be highly observable. The SOC needs telemetry on health and integrity. A sudden spike in authentication failures. Unexpected latency. PEPs running outdated policy versions. Monitor divergence, the expected state. The policy version that should be active and the observed state. The version each PEP is actually running. That telemetry helps the SOC detect direct attacks and subtle control plane attacks. The most common and most damaging architectural failure is the monolithic trap. This occurs when the control plane and the data plane are fused into a single, tightly coupled system. In this anti-pattern, the same piece of software or hardware appliance is responsible for both evaluating policy and enforcing it on the data flow. This design is often chosen for its apparent simplicity. There is only one component to deploy and manage. However, this simplicity masks a deep architectural fragility. When the decision logic and the enforcement mechanism are inseparable, their failure domains are inseparable. Any issue affecting one immediately impacts the other, leaving no room for graceful degradation. Consider a traditional firewall or an all-in-one proxy. The box that inspects the packet is the same box that holds the rule set and makes the decision. If a complex new rule set causes a spike in CPU utilization, the device's ability to forward packets is degraded. A denial-of-service attack targeting the policy evaluation engine becomes a denial-of-service attack on the network itself. At enterprise scale, this monolithic design cannot survive. The blast radius of any single failure, whether a software bug, a misconfiguration, or an attack, is enormous. The system lacks the modularity to isolate faults, creating a brittle architecture where availability and security oppose each other. The architectural diagnosis is a misplaced trust boundary. The system trusts internal components implicitly. There is no contract or secure interface between the decision logic and the enforcement mechanism. This prevents critical resilience patterns. You cannot have the enforcement engine fall back to a cached decision if the decision engine is overloaded, because they share the same CPU and memory resources. The entire construct fails as a single unit. We see mass fail-open scenarios. A bug in the decision process crashes enforcement, which then allows all traffic through. Operational pain is severe and predictable. During an incident, you cannot separate a control plane failure from a data plane attack. SOC teams are left diagnosing a system where every component fails simultaneously. There is often no clean log of the final verdict, just system-level errors. Mitigation requires a fundamental redesign, break the monolith apart, extract decision logic into a separate control plane, refactor enforcement into a lean data plane, and define a resilient contract between them. In conclusion, the architectural separation of control and enforcement is not an academic exercise. It is the fundamental principle for building a resilient and scalable zero-trust system. A correct reference model is one of explicit decoupling. It features a dedicated control plane, ingesting signals managing policy-making decisions. This is distinct from a distributed data plane. Policy enforcement points apply these decisions. These two planes are connected by a well-defined, secure, and observable contract that anticipates failure. This model moves away from brittle, monolithic designs toward a modular architecture where faults can be isolated and resilience can be engineered directly into the system. This is the blueprint for security that survives contact with enterprise-scale and determined adversaries. The primary takeaway for every architect is to rigorously question any synchronous dependency within your security architecture. Hunt down the places where decision logic is tightly coupled with enforcement mechanics and model their failure modes. What happens when the decision source becomes latent or unreachable? Does the system fail open or closed? Is there a degraded mode of operation, and is its logic explicitly codified and tested? If the answer is we don't know, or it fails open, you have identified a critical architectural flaw. The path forward is to redesign these junctions, introducing asynchronicity through mechanisms like signed decisions, capability tokens, intelligent local caching to break the hard dependencies that create fragility. Furthermore, you must shift your focus to the integrity of your inputs and outputs. Make signal provenance a first-class concern. Every signal feeding your policy engine must be validated at its source and its lineage must be traceable. Do not trust, verify. Consciously, you must treat telemetry as a critical feature, not a logging afterthought. Your control plane must produce decision logs that allow an investigator to perfectly reconstruct why a given verdict was rendered. The ability for your SOC and incident response teams to observe, audit, and debug policy execution is as important as the enforcement itself. A system that cannot explain its actions is a system that cannot be trusted under pressure. Ultimately, the challenge is to move from a mindset of static configuration to one of managing dynamic distributed state. Your task is to build a system that is not only secure in its ideal state, but also safe and predictable when it fails. Begin by testing the contracts between your control and enforcement points. Inject latency. Simulate outages. Observe the results. Do your PEPs behave as you expect? The answers will reveal the true resilience of your architecture. Where decision-making and enforcement are conflated, you must redesign the trust boundary. This deliberate decoupling is the definitive architectural move that separates a theoretical security posture from one that is truly operational and defensible in the real world. If you found this helpful, imagine what you'll learn next. Join CyberTechHaus for weekly cybersecurity insights, tools, breakthroughs. Hit subscribe now and stay ahead of every threat.